My name is Ruslan Salakhutdinov. In the US, I go by Russ Salakhutdinov. I thought I'll give you a presentation about the work that we're doing and research a little bit about the past history and such for about 30 minutes or so. And then I would be happy to do a Q&A session. So just a little bit about myself. As was mentioned, I was born in Uzbekistan. I grew up in Tashkent. After I finished my high school, I went to the US and did my bachelor's at a small school in North Carolina. It's called High Point University. Once I finished my bachelor's, I got into PhD program, master's and then PhD program at the University of Toronto up in Canada, where I was doing my PhD in generative modeling and machine learning in general with Geoff Hinton. Then I spent a couple of years at MIT as a postdoc working with a professor called Josh Tenenbaum. And then I came back to Toronto as assistant professor. And in 2016, I moved to Carnegie Mellon University, where I am right now as a professor. So this is sort of my academic path, and I'm still at Toronto, at CMU here in Pittsburgh, Pennsylvania. Just a little bit about my entrepreneurship route. I'm happy to answer questions about this as well. Back in the day when I was at Toronto, I co-founded a startup called Perception Machines with a couple of my students. We worked on deep learning for computer vision, for autonomy. And then we started collaborating with Apple, and then essentially Apple acquired our company. We've talked to Tim Cook, and the decision was made for us to go and actually do the work at Apple. And this is how I ended up at Apple, was the director of AI research, working on different areas, primarily on self-driving cars, computer vision, and then eventually moved into health and Siri. And then, after some time at Apple, I came back to CMU. What's interesting is that a few years ago, my lab started working on agentic models, some of which I'm going to discuss today. These are digital systems, digital agents that can go do interesting things for you. And then the research that we've done at CMU, we had a huge interest from industry. We actually went to Seattle, talked to the Microsoft team. Satya Nadella, the CEO of Microsoft, was very interested. And at the same time, we actually ended up going to Silicon Valley, talking to Mark Zuckerberg, the team here at CMU. And then the decision was made for us to go and do our research at Meta. And this is how I ended up at Meta, essentially doing research on agentic system reasoning and agentic systems. And I've left Meta a few months ago, and together with a couple of friends, we co-founded a startup called Sooth Labs, where I am a chief science officer. And the startup sort of focuses on what we call forecasting engines or forecasting systems using existing AIs to make long-term forecasts. It's an interesting And of course, one of the things that my lab, I also emphasize a couple of things that my lab is working on really two sort of directions, but very combined together. One is the physical AI. So we see a lot of systems that we see today, like Anthropic or OpenAI or Gemini. We think of them as digital agents, right? The digital systems. You can talk to them, you can get the information from them. In parallel, there is a lot of development on what's called physical AI, meaning AI or robotic systems that can actually, or AI systems that can interact in the real world, in the physical world. So for example, you have an agent can take actions, receive observations, states from the environments, and then get the reward. And obviously, to build physical systems, you need to be able to move around autonomously, localize, plan, multimodal input, understanding human speech, reasoning, and so forth. So when we think about physical intelligence, think about agentic system, and the agentic system takes an action. Let's say you observe something in the environment, and then you take an action. Here's an example of what's called the navigation system. So this is a visual navigation system. At this point, that area is fairly close to actually being solved. But obviously, agents need to move around the world physically and require some spatial and semantic understanding of 3D environment. Here's an example. This is an example that was built here at CMU. You're trying to find a potted plant, and there's a little robot that moves around. It builds what's called semantic maps. So it builds the environment of the obstacles, the objects around, so that you can figure out how to navigate in that space. And you can see this little robot. This was an early work that was done. You can see this little robot, and the full vision stack is running on this robot, so it can takes actions, how to turn left, how to turn right, and sort of move around in that space. And what it's actually doing is building this 3D, what we call 3D semantic mapping. As it moves around in the environment, it starts building, what the environment looks like. This is called simultaneous localization and mapping. And also identifying objects around around the environment. So that imagine at some point there's a lot of work where you have a robot. The robot sort of comes to your home, moves around, navigates, and figures out what it needs to be, what it needs to do in your home. So these technologies are getting much more mature at this point, to the point where this problem is actually fairly close to being solved, which is remarkable. Of course, deploying robots in households, like in apartments and such, is still very, very challenging. So one of the other areas that there's a lot of research is on what's models called visual language models, or VLMs, where you're combining vision aspects. So this is what the agent sees environment, plus the language. So for example, I can give you an instruction of what the agent needs to do. So for example, I can say, drop a clean pen on the table. And so the language, there is a language part that comes in. There is a semantic search, which tries to identify what environment do I build, what semantic map do I build, and then it goes to actually taking actions, low-level actions. Like, how do I move 30 centimeters forward? Do I rotate left? Do I rotate right? Right. So these models, and there is like extension of these models called visual language action models, because you're actually trying to take a low-level actions in these robotic systems. And this is what it looks like. This is a simulation environment, right? You sort of ask the instruction, the agent goes and completes sub-goals and builds the environment fully autonomously, right? And the reason why it's called following instructions, because you need to be able to build systems that understand the instruction, have a good language understanding of the instruction, and follow and execute those instructions. Much like in the frontier labs, people are fine-tuning models to do instruction following. You can do the same thing for physical agents. And one of the very sort of exciting areas that people are working on right now is extending these visual language models, or visual language action models, into manipulation, right? And so here's an example of, so let me just go back for a second. Here's an example of the robot trying, to assemble, task is all done and like not very successfully, right? And so these are settings where you're training the robots to actually manipulate objects, which is one of the core areas of robotics that we see today. And just to emphasize, hundreds of millions of dollars go into the startups, go into the frontier labs to build systems that can manipulate objects. Here's an example that we've built here at CMU. I can give an example, put the mouse in the drawer. Success rate is about 90%, obviously not good enough for the real systems, but you can sort of see systems, maybe you're going to have a robot that can cook a meal for you, right? And so placing objects in the pot and then moving things around. Obviously, this is mostly manipulation task, and then generalizing to new novel objects, geometries, and such. So lots and lots of interesting work happening there. I think some of the challenges is building the hardware, hardware, and the ability to manipulate fine grain objects, so small objects. still quite challenging, but you can imagine in the future you're going to have systems that can, for example, cook the meal for you, right? This is still early, so it's going to take a little bit of time, but the progress has been quite strong, at least over the last 5 years. Okay. So digital agents, you can think of them as the same as physical agents, but that operate in a digital space, right? And this is where large language models, I'm sure many of you have heard about large language models. The ability of these models has been spectacular, right? You have zero shot ability. You have something called in context learning. These models have world knowledge. They can generate long and coherent text. They're sensitive to word ordering. And so there's a lot of representation learning that's happening with these large language models. And what we see today, where the technology is moving towards, is building what we call autonomous AI agents. So, and a lot of tasks that you can perform today in a computer will be automated going forward. And a lot of these tasks, tasks that you're doing on the web, there's lots of opportunities to automate these sort of menial tasks, tasks that humans would not want to do, and also augment human capabilities. And for the rest of the talk, I'll focus a little bit more on web kind of tasks, so what we call computer use agentic tasks. So models that can actually control your computer and solve, do tasks that you can do on your computer. So it brings me to the notion of web agents. And you can think of web agents as, one concrete way is that the agent, the AI, sees your screenshot. It also has certain elements associated with the screenshot. That's the observation, right? The observations goes to the agent. The user gives the query what you need to do. The agent does some thinking or reasoning, and then takes the action on the web. And once you take an action, actions of the form like clicking, typing, scrolling, whatever a user would do, whatever you would do on your computer, the agent can basically do the same set of actions, and then it gets into observation. So if you look at this system, agentic system, it's very much similar to what we've seen in the physical systems, right? The agent observes the environment, it takes an action, and then it gets the reward, whether this action was good or bad, and then it takes and then it gets the next observation. So one of the things that we've been looking at recently, and this is the work that that got inspired after we did the work at Meta, because we realized that a lot of agentic systems that we have today actually fail on what we call long horizon tasks. So think about agentic systems that can spend hours trying to solve the task. In the future, we're going to have agentic systems that will spend days solving the task autonomously, right? And we've tried to kind of build those types of environments, and that also thinking, how can we build what we call multi-agent systems or multi-agent environments. And Odysseys is something that we've built here. We've actually collected data from people. So we've tried to identify how people are using the computer. So for example, you want to plan a trip to Palm Spring wedding, you want to search the flights, you want to find the drive time, you want to book the hotel, you want to rent the car, you want to assess like other interesting detours you want to make on your way back, and then you want to build the itinerary, right? And so it sort of requires a very long planning process. And one of the challenges of building these types of systems is evaluation. How do you evaluate whether the system successfully completed the task or not? So in things like math, for example, I'm sure you've seen a lot of examples where AI for math, where AI can solve complex math problems. A lot of these systems are trained on what's called outcome-based reward, meaning that you give it the problem, math problem, the model thinks and gives you the answer. It gives you the answer, and the answer is always either right or wrong. There is no sort of partial kind of correct answer. And you can train these models to actually produce the correct answer. Here, for these kinds of tasks, especially if that requires, humans to, do these, there are many different ways of solving the task. There's no one concrete correct outcome. And so this is where we've built what we call rubric-based evaluation. And the rubric-based evaluation essentially looks at sub-trajectories of the task and says, well, have you actually looked at the flights? Have you figured out what the drive time should be? Have you looked at the rentals? And so as long as you're sort of doing a lot of these things that I'm asking you to do, then I can identify you as being correct. Here's what Claude Opus 4.6 was doing, right? And this is just to show you what existing systems can do. It goes on the web, it sort of looks at the computer science rankings, it goes, creates the Excel spreadsheet. This is all done fully autonomously, which is actually very remarkable. It goes through faculty, some of these faculty I know. It sort of like tries to go through different schools and looks for PhD programs, looks who's looking for PhD, who's looking for students, and areas. And so you can, a lot of professors that it's looking at, I'm actually able to identify. This is sort of an example where it solves, but it doesn't fully solve the task. So this would be almost a task that solved partially, right? And so, and these are rubrics that you can decide to evaluate how good the model's done, right? Has it looked at, has it looked at the 25 top US schools? Has it looked at the faculty directories? Has it looked at the personal web pages and so forth? And what we see is that a lot of frontier models are solving tasks, what we call perfect, meaning that, has it actually completed all the rubrics-based judges? So has it actually successfully solved the task? About 53% of the task is actually doing, which is actually very strong because we don't think humans will get to that level either. So machines right now, some of these long horizon tasks, I think they are on par with humans or can do better than humans. What's interesting is that you can see the difficulty for easy tasks. Frontier models are at almost 100%. So simple things existing models can do. Hard tasks that require you to actually do reasoning and thinking and search for a lot of different details, models cannot do. But this would also be very hard for um, uh, humans as well. When I was applying for postdoc positions, I think I've spent at least a week looking for who is looking, who is hiring, who is, and so as you can imagine, those kinds of things are going to be replaced by computers. And obviously, as the step budget, how many steps, how many actions the agent takes, models typically tend to plateau around 100 steps, but even the best models sort of take more than 30 minutes at this point, and they become very expensive. One of the interesting things that we found is that on the failure analysis is that Opus, for example, this is Claude model, Anthropic's model, it sort of tries to overinvest in research and tries to gather information without actually producing the final outcome. So it does a lot of research, but doesn't produce the outcome. GPT fails through inaction. So it generates the report and sort of plans, but then it doesn't fails to actually execute. For long horizon tasks, both models tend to stall in early stages, right? So one of the issues is that things that require very long again, these are very long horizon tasks that requires for example, I want to visit like 30 different restaurants. So I want to visit 30 different universities. Then these models tend to get stalled in gathering information and sort of trying to basically failing. So it's reasoning. On the other hand, we found very interesting capabilities. So for example, GPT, when it looks at broken web pages, it tries to extract structured data and metadata. So when you see when the HTML when the web page is broken, you can't see it. It's trying to actually look at HTML and try to get from the source and tries to extract information behind the source. Opus shows complementary stacks. What it does, it tries to bypass access issues. For example, you have 403 error. It tries to go to archive with a Wayback Machine and tries to retrieve the data from the archive, right? So for example, you can recover class schedule information that would not be available through direct browsing. And this also, interestingly enough, raises issues such as safety, right? I go to the web page, I have photo 3 error, I can't see it. Any reasonable human would say, okay, the information doesn't exist. Frontier models are trying to kind of like almost like try to bypass this. They either try to look at raw HTML or they try to look at the archive data. They still trying to figure out, can they get the information? This is something that interesting enough because, for safety sort of critical applications, these models will try to go around, right, and retrieve or try to get the information that otherwise would not be available. And the last part I want to briefly mention is the multi-agent settings. What I've talked about is agentic systems that can, they try, but a lot of times they would fail, right? Single agents, they sequential, they inefficient, they struggle on long horizon tasks. What you really need is you need systems that can decompose, you can parallelize, and you can replan. And this is what our first attempt at building these, what we call multi-agent computer use systems, where you give a user task. There is a manager, think of it as a frontier model, that initializes what we call a direct acyclic graph, a DAG of what tasks you need to do. And in what order. So it does the reasoning, it does the planning, and then you instantiate multiple agentic systems. These could be small agents, and then they go and execute subtasks. And then the manager aggregates that information and decides whether you need to redo some tasks or whether the task is complete, and then you go to the next subtask. But the idea is that at the high level, you have a manager system that kind of coordinates these local agents. And these local agents, they go solve the tasks, they come back to you, and the manager can replan. Here's an example of where you have an attempt to go through GUI interface. I think here you're trying to do something to the image, like adjusting the brightness and adjusting the color, the background color. And the point here is that the agent goes through the GUI interface. It's trying to go through GIMP in this case, trying to switch. It fails. It goes through command line interface. It fails. It recovers. It launches recovery attempts, which is interesting enough because the manager says, look, I haven't solved this task. Try to recover. If you fail, try again. And then it revises a new strategy and another command line interface attempt, and then it solves the task successfully, right? So you imagine these systems where the agents would go, and if they fail, they'll try to attempt to solve the task again. And this is the beauty of the multi-agent systems, because you can have two parallel agents trying to solve the task. If one of them fails, the other might succeed. If they both fail, the manager can refine the strategy, refine the reasoning, and then go and try it again. And what we see is that across multiple different data sets, a lot of times, you have positive improvement in success, right? On Odysseys, these are probably the most challenging one. You have significant improvement in performance. And this is just to say that more effective test time scaling. So these systems, the multi-agent systems, can be much more effective in test time, meaning that they can spawn different sub-agents, try to solve the task, come back. If they can't, condition on this information, you spawn new sub-agents, and then they can solve the task. And so again, here, just wanted to show you that single agent versus multi-agent. And so anytime you have success of a single agent with multi-agent framework, you can actually do much better. And obviously, parallelization saves times. One interesting thing is that we've seen that agentic systems fail to do planning. This is one of the biggest issues, especially for tasks that require you many hours to solve. And we see that replanning here becomes critical. So what that means is that you have a manager system with sub-agents that can replan. It can significantly improve the accuracy. So for example, we see examples of something like MapReduce, parallel information gathering. So I'm trying to get some information. I can dispatch multiple agents to go gather this information, retry an exploration. If the agents fail, I can set another agents to go try to explore and then come back. And what's interesting is that we found, in terms of the key findings, is that these multi-agent systems, they achieve test time scaling through parallelism and multi-agent coordination. So running parallel and coordination. The strongest gains we saw comes from continuously replanning. So if the agent fails, it continuously replan and does the parallel execution of specialized subagents. Multi-agent coordination also, interestingly enough, enables recovery from failures. And that's important because a lot of previous systems, they would go, they would try something, they would fail, and then they would not know how to recover from the failures. These multi-agent systems have the ability, because you can parallelize and you can replan, to recover from failures. And this is something that we're beginning to see. It's very early in the research. And obviously the framework is agnostic and can integrate multiple. That these are students, amazing students who are doing all the work. These are students in my lab. And just very briefly, I do want to mention some of the recent lab members. A lot of students from my lab actually go to the universities. Ben Eisenbach is now a professor at Princeton. Paul is a professor at MIT. Ruslan, professor at Peking University. Buwan is a professor at Duke. Roger is at Toronto. Alex is at UIUC. So these are sort of, quite, I think that a third of my students tend to go to academia. Obviously, there's a lot of pull into big tech. So a lot of students do go into, Tesla, Meta, Microsoft, Google DeepMind, NVIDIA. So these are sort of Microsoft Research. These are sort of a lot of students that graduate from CMU. They end up going to the big frontier research labs. And actually, quite a few students go to startups, which is a work at the startups. I think one of the notable example is Ziling Yang. He was a student here at CMU, my student at CMU. He's a founder and CEO of Moonshot AI. If you know about models like Kimi models that are frontier models in China, that's basically he's a co-founder and a founder and CEO of Moonshot AI. And obviously, you have students who went to co-found different startups via robotics, and some students actually do end up going into some of the startup friends that